doesn't look like there are any clarifying questions, so let me just quickly introduce our next speaker. It's Dr. Alla Zelenuk. She got a PhD in chemical physics from the Moscow Institute of Physics and Technology in Russia. She's currently a senior scientist at the Pacific Northwest National Laboratory, and her expertise is in atmospheric transformation of nanoparticles and developing instrumentation to study them.
And thank you very much to the organizers for inviting me here and giving me opportunity to tell you a little bit about our research and to serve together with the rest of the panel as a panelist in this meeting. I'm a physical chemist, and my research is focused on the development and application of unique tools and methods to characterize small particles, which include both fine and ultrafine particles. You already heard that small particles are ubiquitous both in human-made and in natural environment. Nanoparticles are used in nanotechnology, and nanotechnology gave enormous rise to nanotoxicology. Atmospheric particles, which we study, greatly impact air quality, visibility, and health, affect climate, and many, as you heard, of these particles are emitted by cars. And characterization of small particles is rather challenging. They come in a variety of different sizes, composition, phase. Here you could see more of microscopic images and cartoons of particles which we very recently studied. And you could see just from the pictures that properties and effects of these particles will be very, very different. So a couple of years ago, National Academy of Science actually were hosting workshop on challenges in nanoparticle characterization, in small particle characterization. And I was invited to show our way of doing things. So instead of trying to use different tools to characterize assembly of particles, different mixtures of particles, and then try to connect the dots, basically, try to correlate all these measurements, what we are trying to do, to look at one small particle at a time and characterize as many of its relevant properties as possible. Our main tool is single particle mass spectrometer. Many people refer to me like Splat lady. We have instrument Splat, Splat2, mini Splat now. This instrument we use both in the laboratory and we're taking it outside the lab. We are taking it to engine test cells. We are taking it on board of the aircraft. Here you could see a picture of instrument flying on the aircraft in Arctic, trying to understand where pollution in the Arctic is coming from. And over the years, we developed different ways to characterize many properties of particles: number, concentration, size, density, mass, different aspects of particle shape, composition, morphology. This list, we keep working and increasing it continuously depending on the questions we are trying to address. And today I would like to show you a few of the examples where we applied our instrumentation to characterize particles, atmospheric particles, and particles emitted by different engines. And I will start with diesel engines. Here we are looking at emissions from 2-liter Mercedes engine, from little red car. And you could see that majority of these particles are composed of fractal soot particles, which dominates, composition of which dominates by elemental carbon, but they have some pHs. In this case, to see these pHs, we had to zoom in by a factor of 1,000 because these particles, and in this majority, contribute to 90% approximately of total number of particles. They contain approximately 1% of pHs, and their size distribution peaks, aerodynamic size distribution, around 100 nanometers or so, and they look like this. These fractal soot particles is comprised of this many little spherules. We could calculate their mass, determine the size of these primary spherules, number of spherules per aggregate of different size, surface area, which is very important when we're thinking about health effect of these particles. Look at the different coatings on top of these particles. And from our atmospheric studies, we know that when these particles are emitted, they change in atmosphere. They become coated by secondary organic aerosols, by sulfate. Their structure is changing, they become collapsed. And as a result, their optical properties and overall properties are changing. The rest 10% of particles have very different composition, different shapes, different size distribution. Here are just two examples of particles containing PAHs and very toxic nitro-PAHs. In this case, to see these PAHs, I even didn't have to zoom in and look at their contribution because they dominate the composition of these particles. And you could see that they come on much larger than soot. I'm shading it in this gray area just to show the difference in size, on much larger compact particles. And another way of looking at these things as composition of these exhaust particles as function of size is shown here down on the slide. And you could see that small particles are mostly dominated by elemental carbon. And PAHs, nitro-PAHs, organic, some inorganic comes on these larger compact particles. Many of you know that car manufacturer company received this mandate to produce high-efficiency, new generation, fuel-neutral engines. And in collaboration with General Motors and University of Wisconsin, we looked at several of such engines. Two examples of spark ignition direct injection DC and gasoline direct injection compression ignition GDI-CI engines. There are two examples of gasoline engine technologies which have potential to achieve significant increase in fuel efficiency by operating more like diesel engines. And diesel technology is right now already applied in many light-duty passenger vehicles, and indeed it offers increased fuel economy, but it also produces large number concentration of particles, which represents clearly large challenge. GDI-CI engine is low temperature combustion strategy. By carefully tailoring the injection, fuel is injected in 2 or even 3 small injection, and timing between injection and ignition, one can reduce both concentration of NOx and particles. So here, just a couple of examples. We looked at emissions by diesel engines operated under a range of different operating conditions and fuels. And here on the top, you could see number concentration for 3 different fuels: black EEE gasoline fuels, E20 fuel, which contained 20% of ethanol, and E85, which contained 85% of ethanol. And you could see that E85 produced nearly 2 orders of magnitude fewer particulates than E20 and EEE regular gasoline engine. What we find when we look at composition of these particles, that they contain significant fraction of organics, between 40 to 60%, and this is for 3 different fuels for different operating conditions, ratio of organic carbon and elemental carbon in the particles. And white shaded boxes shows contribution of PAHs. So you could see that organics contribute between 40 to 60%, and PAHs contribute to large fraction of this organic component in the particles. But what we found when we tried to heat up these particles using this European protocol for removal of organic exhaust emissions, that this organic is impossible to remove by sending them through thermodenude or evaporative chamber. This organic is tightly bound within these primary spherules, which comprises soot agglomerates, and it's impossible to remove it. We also found that unlike diesel engines, the size of these primary spherules is changing depending on fuel, depending on engine operative conditions, and sometimes for the same conditions you could see agglomerates made out of small spherules and large spherules. And we trace this population to different heterogeneities in richness of the fuel in combustion chamber. And I would like to point out that this E85 condition actually produces the smallest size of primary spherules. And all of these findings about this drastic difference between particulate produced by diesel engines and DC engines call for reconsidering what kind of after-treatment is appropriate to reduce particulate emissions and the environmental impact. A few results on characterization of GDCI exhaust particulate. In this case, we find that engine load has enormous impact on number concentration and properties of particles emitted by this engine. Here, for example, this set of lines shows low load conditions. You could see that particles are very small. There are many, many ultrafine particles, and they're tailing off towards larger particles. At high loads, you could see particles, number concentration are much higher, and they're much larger. So mass of emitted particles is very, very large. And when we looked at the composition of these particles, we find that under low load conditions, 70% of particles are compact organic particles, and 30% are fractal soot particles made of 40 nanometers spherules. Under high load condition, nearly all particles are fractal agglomerates, and the soot agglomerates contain 40 to 45% of organics, and again, pHs contribute to large fraction between 20 to 25% of organics in these fractal particles. Elizabeth already mentioned that when particles are emitted by the cars, they come not only in particle phase, but also in the gas phase. And Stacy showed you that the gas phase pHs get reacted and disappear very fast. But some of these gas phase pHs get incorporated in other type of organic particles and get transported far, far away from the sources. And when we looked at composition of atmospheric particles, what we find that organic aerosol contribute to very large fraction. Here measurements from aircraft deployment of our instrument when we were flying over Cape Cod and we were measuring composition and size of individual particles. What we found that majority of these particles are organics. All of this green shows organics. You see some soot particles showing in black, biomass burning particles showing in yellow, but vast majority of these particles, in some places up to 90% of fine particle mass comes from organic particles, composed of organics. And majority of these organic particles are secondary organic particles. You already heard today the term SOA, which comes from the fact that these particles not directly emitted in the atmosphere, but when volatile organics, either from trees pollute, you heard it back from in Reagan time, and from the cars get oxidized, they form either new particles or they get condensed on some pre-existing particles in atmosphere. So what we found in our recent study, that the gas phase pHs can get acquired by secondary organic particles during their formation, and they become trapped inside of highly viscous SOA particles. And because they become trapped, they're shielded. They're shielded from evaporation, and they're shielded from oxidation. And this way, they could get transported far away from the sources. Perhaps then it's not surprising that in pristine environments like in Arctic, gas phase concentration of pHs are orders of magnitude lower than in China or in Europe. But in particle form, it's nearly the same as close to the sources. In contrast, when pHs just sit on top of the particles, they evaporate completely and very fast. So this data provide explanation for long-range transport of toxic substances like pHs and perhaps other persistent organic pollutants regulated by EPA. And we also found the synergy between these SOA particles and pHs, in which as SOA particles serve as the vessels for pHs to get transported far away from the sources, pHs reduce evaporation rates of SOA particles and increase their formation yields and atmospheric lifetime. And with this, I would like just to switch to summary slides, basically pointing that life is complicated. Particles, even from mobile sources, their properties strongly depends on engine type, fuel, and engine operative conditions, which greatly impact all their properties: number, concentration, mass, load, and composition, shape, morphology. And what we find that nearly all exhaust particles contain pHs. How much and in which form, where they are on particles depends again on engine, fuel, and operative conditions. And secondary organic particles play enormous role. This is the small particles Elizabeth was talking about in long transport and longer atmospheric lifetimes of pHs. Thank you.
Thank you for that talk. I'm happy to introduce our last speaker today in the first session, and it's Dr. Andre Nell. He's a professor and a practicing allergist and immunologist at UCLA. He's the director of the University of California Center of Environmental Impact of Nanotechnology, and all sorts of other titles. Let's see, his degree is from...
I have a medical degree from Cape Town, South Africa,
Great.
PhD from the University of Cape Town.
Great, thank you. All right, welcome.
Thank you. Well, I thank the organizers for the opportunity to say a few words. Now, I think you've heard a lot about the science as of where it stands. So give me a little bit of orientation before I show you some of the data which we have generated when we still had a particle center. The genesis of where we stand is a 1998 NRC report that asked for a blueprint for research on airborne particulate matter. And in that blueprint, it was called out the need to understand the role of ultrafine particles as a priority PM. Based on that, research programs were initiated up to 2008. And in 2009, US EPA Integrated Science Assessment concluded that there's inadequate evidence to determine a causal relationship between short-term ultrafine exposures and mortality or central nervous effects. That the evidence was suggestion of short-term exposure effects, that there was inadequate evidence for long-term exposures, and that epidemiological studies suggesting that cardiovascular effects, and I emphasize the word associated, I'll come back to that, were smaller particles, but few reports have established a link between ultrafine particles and increased mortality. Now, in 2013, the Health Effects Institute, in their executive summary, basically concluded the same, and it says, while selected study shows evidence of effects, the current evidence, when considered together, is not sufficiently strong to conclude that short-term exposures have effects that are dramatically different from those of larger particles. And they say there were limitations and inconsistencies in the research on ultrafine particles. There were no long-term animal studies, and that relatively few studies have compared ultrafine with other particle types. In a 2012 report to Congress on black carbon, I think this publication probably came out only in 2012, EPA advised that black carbon is a component of both fine and coarse particulate matter, though because of its small size, it is mostly associated with a fine PM2 fraction. And most of the literature evaluating the potential impacts of BC on human health and the health benefits of mitigation has focused on black carbon as part of PM2.5. And in that entire report, in the, at least the health effects, the word ultrafine does not appear a single time. In the entire report, the word ultrafine appears 4 times on 2 occasions, of which it is citations of papers. The executive summary also said that EPA has determined that there is insufficient information at present to differentiate the health effects of the various constituents of PM2.5, and concluded that it is noteworthy that emissions and ambient concentrations of directly emitted PM2.5, again emphasis on directly emitted PM2.5, are often highest in urban areas. Now, what I show you here is collected on the roof of the engineering building at UCLA, where I show you one composition of an ultrafine, of a fine particle, a PM2.5. There probably be many different types, and as you can see, what you see in that particle is that it mostly consists of crustal elements, salts, etc. And then mixed with it, you see these stringy soot particles, which are probably ultrafine particles that have collected. So this is now representative of a whole series of PM2.5 particles, which is the current basis for regulation. I now show you collected also at UCLA a transmission electromicrograph of the ultrafine particles, and you heard about fractal soot. So what you see here are fractal soot particles, which is the main source of emission of particles from vehicular traffic. We're close to the 405 freeway, and the condensation of vapors. And the major toxicological component of this is organic carbon, of which the semi-volatile organic components, such as the PAHs and perhaps the metals, play the major role in the toxicology. And as you've heard, there are many different sources, including diesel, and these particles, of course, are not regulated. Now, this is just one slide, therefore, showing you that if you now compare PM2.5 to ultrafine particles, you've heard this over and over, just based on composition alone, there is a clear difference in the organic carbon fraction, which contains the semi-volatile organic carbons, so that in these fractal particles, the carbon core is wrapped in a core of the organic chemicals and some of the metals, which in our opinion is the basis of the toxicology of ultrafine particles. So if I now have to tell you my personal opinion about PM2.5 assessment, I would say that the assessment do not adequately address the hazard of ultrafine particles and vehicular emissions. And the first point is that the toxicology of ultrafine particles may differ from the toxicology of PM2.5. Second is that the constituents more strongly associated with PM2.5 may appear to be more closely related to the adverse health effects than other constituents, even if they are not inherently more toxic. In a recent study that came from Harvard, where they assessed the association of stroke with greater Boston area PM2.5 and measured 18 PM2.5 species, you can see that a significant finding was that although there was an association with PM2.5, many of the constituents of PM2.5 had no direct relationship, but the elemental or black carbon did have an association that was even stronger than PM2.5. So importantly, this study has clearly indicated that the constituents that are more strongly correlated with PM2.5 may appear more closely related to the adverse health outcomes than other constituents, even if they are not inherently more toxic. Therefore, it's important to properly account for potential confounding effects when using PM2.5. Another significant finding was going back and looking at the issue of statistics. And I bring you back to that word because a constituent is emitted from several sources and a single source emits several pollutants. We cannot distinguish between the independent toxicity of correlated components in an observational study. Findings on health risk associated with a given constituent may represent the toxicity of that compound. It may serve as a marker of other compounds that co-vary with the constituent of interest, or it may represent the combination of the independent toxicity and interaction of co-varying constituents. And next point I want to try to make for you also in studying this, that the pulmonary retention and regional impact of ultrafine particles differ from PM2.5. Ultrafine particles are much smaller, they go deeper into the lung, and they are retained at a 50 to 60% efficiency as compared to most PM2.5, which are exhaled. And this has therefore profound implications when you're doing dosimetry studies, because the ultrafine particle is likely to go to the sites of where the pathophysiology of disease is more important. Use of a single exposure metric is inadequate for elucidating all the exposure response dynamics of a mix of particles included under PM2.5. Ultrafine particles vary dynamically in terms of the semi-volatile composition and exert a range of toxicity in urban areas that cannot be delineated by mass only. Subsequent research have also now shown that particle number is consistently associated with cardiovascular effects. There was a World Health Organization report that contrasted the EPA report on black carbon, explaining that black carbon is one of many PM species present under the PM 2.5 umbrella. And finally, in my opinion, there, as we've seen from the previous discussion by Dr. Alla, that there are questions about the control of emissions by modern diesel engines that leads to improved safety because of the complexities as outlined. So I'll just show you here one recent paper of Diesel Suit, which identifies from this publication from Dr. Benjamin Frank that the major question arises whether the emission of modern diesel engines are characterized by a potentially greater threat to human beings. And the answer is not straightforward. It's clearly complicated. But what they clearly show that in the EU low emission program development, that the chemical activation of the diesel, the DPM, is astonishing. And some of the structural and chemical features which are shown by the low emission DPM shows that not only do the particles become smaller, but you see the formation of these graphite surfaces with defects with highly conjugated type of chemistry called pi electrons that anchors functional groups, including toxicity materials. So our own research have shown, we followed the hypothesis that ultrafine particles may actually be responsible for the majority of observed health effects in polluted urban environments, and the mechanism is the presence of the semi-volatile organic components, which constitutes an important component that is responsible for biologically mediated oxidant injury that leads to the excitation of inflammation. We set up measurement equipment when we still had the center to do so near freeways, so we actually did measure inhalation. We developed constant particle concentrators to separate the ultrafine particles from fine particles. It was unfortunately the fine PM 2.5 still contained ultrafine, so that confounded our effect. There is some effect on the size distribution of these ultrafines from what is emitted, but nonetheless, we were able to gather very important information. Number one is that ultrafine particles are very high on the roadways and then drops off around with increased distance from the freeway. So in Los Angeles, we are not fortunate enough. In most aspects of the city, we are in close proximity. We've developed assays that can quantify the degree of redox activity of ultrafine particles. We've applied this to measurements of many different particle collections, to ultrafine, a combination then of the fine plus ultrafine collections and coarse particles throughout the city. And these indicators showed in most cases that if you look at the oxidant potential measured by that assay that we developed, the DTT assay, that the pro-oxidant effect of ultrafines was consistently higher than that of the mix or the coarse particles. We've shown that that activity correlates with the organic carbon and PHA content. We've shown that at biological level, assays for oxidant injury also shows that the ultrafine particles are more proactive than the other particle sizes. We've done animal exposure studies in animals which are atherosclerosis prone, and we're able to show that there's clearly an increase in short-term exposures of atherosclerosis, including the size of atherosclerosis plaques. We've been able to show that if you image the oxidative stress in the lung of an animal, that the animals exposed to the ultrafine particles clearly show a signature in the lung, where the particles are inhaled deep into the lung and reside in subcellular places such as the mitochondrion, which is a site notorious for oxygen radical generation. Our asthma study showed that the inhalation of ultrafine particles deep into the lung at a site where immune activation occurs excites the equivalent of more allergic inflammation. On doing correlations of the assays that we had, we could show that there's a much higher correlation between the elemental carbon, nitrate. The organic carbon compounds had a much stronger correlation with the pro-oxidant capability of these particles. And when we corrected that for pH 8 size, the pro-oxidant effects was more reflected in the higher molecular weight PAHs. So I conclude in just showing for you, I unfortunately could not find my slide at the end of 2008, but at 2006 point, the Southern California Particle Center had published more than 200 publications on ultrafine particles, which included development of mobile size-selective PM concentrators for doing the work, characterization of the formation and dynamics of particulate matter near freeways, developed chemical assays to refine redox activity, demonstrated that pro-oxidative chemicals induce hierarchical oxidative stress effects which relate to airway inflammation, described that there's increased propensity to drive allergic effects, conducted human clinical studies using coarse, fine, and ultrafine particles in which we did comparisons and where the ultrafines clearly showed a signature, and participated in some of the epidemiological studies on the role of traffic density and asthma and developmental effects, of which you will hear later in the clinical session. Thank you.
Thank you. Great. Well, so we've got about 40 minutes left, and so we've sort of the speakers have been able to, sort of present some of the background and some of their results, and now we're going to open up for questions. And I think the first thing we want to try to do is to just open it up to the panelists to see if there was any reaction to each other's sort of presentations or things that you want to sort of highlight before we, get into the questions from the audience and the questions from me. Were there any comments that you wanted to make in terms of on each other's presentations, or any points that you want to emphasize? Nope, it sounds like everybody's feeling pretty comfortable.
Everyone in agreement?
All right, well, great. Well, I have a stack of cards up here, and if folks also want to come up to the microphone if they want to say something, that would be useful as well. So I guess maybe we'll sort of organize the questions here. I just got a bunch of them, so I'll need to look at them for a second. Why don't we start with Dr. Nussbaum? Yeah.
Anyway, Linda Birnbaum. I was just going to say the National Toxicology Program is conducting and designing large series of studies using up to 70 different pHs, including a lot of the nitro and the oxy and the hydroxy, and we will have analytical standards for these, which we'll be happy to make available. And one of the parts of this is to look at the fact that you never have any one PAH in isolation, but in fact you have mixtures, so that we will be doing mixture studies here.
Great. Well, let me just sort of try to organize some of the questions here from the cards. And so maybe we'll just start with sources. And I'll just throw this out there to anybody who wants to answer it, but I can direct it at a specific person if we're not getting an answer. So the first is, there's been a lot of discussion that combustion is an important source of pHs. Are there important non-combustion sources that folks should be aware of? That didn't come out much here, and someone was concerned about that, and in particular around the oil and gas development or unconventional gas. Does anybody want to comment on non-combustion related sources of pHs?
Well, I think that it is very important to be aware of the effect of in-house or indoor combustion sources that can contribute to the formation of ultrafine particles and secondary particles. Cooking, for instance, is a common cause. And then we also are faced with wood burning as an important source, which contributes in some cases. Very importantly, I heard Montreal this morning. That's an important potential source. We also have forest fires, volcanoes, so there are indeed combustion sources that are non-combustion sources that are important. And then I also just want to mention that for combustion sources, we do not, that we also keep in mind what happens around airports, where also the jet fuel components do generate a huge amount of particulate matter in the ultrafine particle size range, and the same goes for shipping, where the Los Angeles port certainly also contributes regionally to very important.
Does anybody want to add something? Stacy?
I would just add that we've been talking about pyrogenic PAHs, but many of them can also be petrogenic PAHs. You know, Gulf oil spill would be an example of that.
Dr. Costas?
I would just add, you know, we heard some of this morning already, that, you know, secondary organic aerosols, you know, move along this cascade of production of PAHs. And, you know, it's interesting, adding to the complexity of this, you know, we've heard, what's the role of biogenic around forests? You know, there's lots of emissions. Anne-Marie Carlton of Rutgers, when she was with EPA, did a really impressive modeling study that showed that biogenic formation of SOA was enhanced by the contribution of the anthropogenic component. So yes, maybe it is the trees, but the trees are activated, if you will, not the trees themselves, but the chemistry by the precursors that we heard about this morning that are so labile.
Great, thank you. I guess no one responded on the oil and gas component. I mean, there was a mention of leakage. Certainly there's lots of combustion-related activities associated with producing that gas, whether or not it's diesel-powered equipment and things like that, that certainly will emit PAHs. Here's a question about sort of lifetimes and trying to interpret the data. And people are thinking about the lifetimes of ultrafine particles and PAHs. And do they remain airborne longer than previously thought? I mean, we were talking about long-range transport, and I think people are convolving both the ultrafine particles and PAHs. So does someone want to comment on the sort of lifetimes of these different types of compounds or pollutants in the atmosphere? Stacy? I think this one was directed at you, but...
Yeah, I would agree that we're realizing they're longer. Well, PAHs on fine particles are longer lived in the atmosphere than we had traditionally thought. I think that's evidence from our transport studies, trans-Pacific transport, 5 to 7 days time. But it's also been observed in Europe and the Arctic to some degree. So along with my laboratory studies in the environment, other people have also now seen it.
Anybody else want to add? I mean, certainly PAHs have a very long lifetime, but ultrafine particles people generally view as being pretty dynamic.
With PAHs, you also have the potential for re-emission, where deposited PAHs can stay for a while and the temperature heats them up, and then they move along again, so that you have this cycling that occurs separate from their degradation.
Great. Maybe we'll take one from the microphone here.
Jim Zhang from Duke University. I have a question regarding nitro PAHs. I think, Stacy, you showed photochemistry, how that contributed to the formation of nitro PAHs. And also, I think, Ala, you talked about the diesel generation. And we know that certain nitro PAH isomers are specific to some combustion conditions, meaning diesel engine-related emissions. So with the new engines, is that sort of isomer changes with the new technology, or what's the in the atmosphere for both of you? I think question is, in the atmosphere, how much you would think is directly coming from thermal generation, nitro PAHs, or how much is from nitro photochemically generated nitro PAHs?
We just have experience with characterization of these test engines, and we indeed observe nitro PAHs coming from diesel engines, but we did not observe nitro PAHs coming from this new generation fuel neutral engine. And one reason can be because they're low temperature combustion engines. No, I'm not an engine person, but I could just comment on the observations that most of nitro PAHs we observe from diesel engines.
I think I would add that we were discussing this at dinner last night, but these compounds we're talking about are not new. They've been around since the advent of fire. In some cases, we're just now developing the analytical techniques and have standards available to start to look for them. That's one thing. The other is that, I think some of the isomers of nitro-PAHs are formed primarily from gas phase reaction, some from heterogeneous reaction. So in the case of nitro-PAHs, there are some specific isomers that come from either one or the other.
Can I make a comment? So I'm going to make the comment about oxy-PAHs, because I do think that atmospheric conditions and photochemistry contribute to the formation of those. And in the studies that I've just mentioned, I didn't have time to say that the oxy-PAHs in derivative forms, such as quinones, if you do the toxicology of these particles, at least those play a very important role in the known pathways by which the semi-volatile organics can engage inflammatory pathways in the lung and possibly also the cardiovascular system. And in that regards, the measurements done by the Southern California Particle Center have clearly shown that there is a trajectory of effects that starts near the coast, and as you go inland, the atmospheric transformation and conversion to oxy-PAHs gets worse and worse till you get up to Riverside, where for the same number of ultrafine particles, the effects becomes accentuated due to the oxidation process.
Great. All right. So here, thinking about. We'll do
Hi, Alan. It's Katie Walker from the Health Effects Institute, and I wanted just to add a couple comments and perhaps an answer to Jim Zhang's question about emissions from the newer diesel engines. I'm with the Health Effects Institute and with the Collaborative Research Center and a number of other collaborators did work characterizing the emissions of the newest diesel engines starting in 2007 and also in 2010. But what you do see is enormous reductions in emissions of PAHs and the nitro-PAHs, 90, 99% reductions in the emissions. And we're just wrapping up the toxicity studies in long-term animal studies with exposures to those and are seeing no tumor formation. But the work out of the Collaborative Research Center, also HEI's reports, are great resources for really looking at what those emissions are from the newer diesel engines. And as we sort of think going forward about policy changes, we also need to be thinking about the changing mix of technology in our systems. I mean, you've raised the ones about the DISI and GDI, and that's a part of this story as well. But just not to forget that we're now something like 30% of heavy-duty diesel engines are this new technology, and that's just in the last 5 years or so. So another thing to take into account as you go forward thinking about this.
Great. So here's a question about health effects, and so this is addressed to Dr. Nell, and it's how well does your DTT assay reflect the sort of non-pH components of PM, such as transition metals? If not, does the correlation between DTT response and the sort of carbonaceous fraction EC and OC reflect just the fact that the pHs are formed, as part of the sort of soot formation process? So it's a question about the sensitivity and discrimination of that test.
Well, I think I do not think it is a test that is anywhere near specific for PAHs, but it is a test that reflects the pro-oxidant activity that is present as part of the organic carbon compounds. In order to dissect that out further, John Freund and Art Cho also developed technologies to try to implicate the contribution of metals, to implicate the contributions of quinones and oxidized PAHs, and have also come up then with a readout test that could reflect different types of pro-oxidant substances. The DTT assay was set up as a initial measure to study the oxidant stress response. The natural progression of taking it to a point where it becomes component specific are the types of technologies that now needs to be developed to reflect for us whether we can see biomarkers or groups of biomarkers being reflected in that. I don't think the technology is there yet.
Great. Anybody else want to chime in on that one? I wanted to follow up just a question. I was reading through the sets of questions we have here, and one is the thing we wanted to talk a little bit about trends and what the trends in sort of atmospheric concentrations are. And you spoke a little bit about the trends in Canada. Does anybody want to say something about what the trends here? This is follow up to the point that the new diesel engines, the emissions are a lot lower, but what are the atmospheric trends doing of these PHs and ultrafines? Does someone want to comment on that in the United States? Does anybody know? That was one of our kind of charge questions.
I guess I'll make a couple comments, and not necessarily so much on the trends, because I don't have, there isn't a really good data source for that. But it's kind of interesting in the chemistry that, or the physics, that when you have an air pollution episode, when fine particles increase, the primary agglomeration particle for ultrafines is the accumulation mode, or the fine particle. So in fact, when we have air pollution episodes where we measure lots of these health effects, we have the fine particles go up, but the ultrafine particles actually go down. So whether that relates to something being carried into the lung on these fine particles, or whether it shows that ultrafine particles aren't playing that much of a role is unclear. When we make comparisons sometimes of the pro-oxidant activity of fine particles versus ultrafine versus coarse, it's always done on a mass basis. And the mass component of ultrafine particles in a collection of particles is very, very small. So if you adjust for the distribution of the particle amount there, the contribution to the total oxidant activity may be very, very small. But again, those remain the questions that we really don't know. If you're in an environment that's dominated by ultrafine particles, perhaps near the road, the conditions are changing.
Do you want to add something?
Just about the trends.
Yep.
For PAHs. Actually, when we were doing our modeling exercise and trying to find data to compare the model output to, Canada has a network that's long-standing across the country looking at PAHs, but there was no similar network that was providing data on the American side. So we were able to find data from California. The California Air Resources Board has a network, and through IADN, the Integrated Atmospheric Deposition Network, but that only has a few sites in the Great Lakes region. I understand that more recently there's a new National Air Toxics Monitoring program, which does include PAHs, so you will be able to look at those trends from now on.
Dr. Nell?
No, so I cannot answer specifically about PAHs. I can tell you just that Costas Saoudis has done enormous numbers of PAH measurements in different trajectories across Los Angeles, and there's a rich data set that do indicate that various different combustion vehicular resources do contribute significantly to the generation of PAHs that you can measure at those sites. So it's a rich body of literature, so I cannot summarize that in one sentence. What I can tell you, in a city like Los Angeles, that near roadway health effects are real. And the impact, therefore, of not having a metric for assessing ultrafine particles in a city like Los Angeles probably means that a lot of our attribution of what it is to near roadway health is not going to be properly interpreted until that type of standard and measurement is implemented in urban areas.
Dr. Simnich, you want to?
I would just add that, in general, the PAH emissions have gone down in developed countries and have increased in developing countries and may have peaked in China. We don't know yet. But on the ultrafine particles, there's not enough data to know that trend.
So, I mean, one of the questions we're going to get to here is research needs, but it seems like for both of these classes of pollutants, there's some data gaps in terms of assessing trends and things like that, but we'll get to that in a second. Dr. Bailey?
Chad Bailey from the EPA. I guess I can't speak to long-term PAH trends in the U.S., but we're talking about pyrogenic PAHs a lot here, and one of the endpoints of pyrogenesis is soot, and EPA does have fairly long-term monitoring trends for black carbon. And if you look at the improved network, which started in national parks years and years ago. There's a long-term trend over time. Going back beyond when the EPA, when the Improve Interagency Network started, long time ago, there's this thing called coefficient of haze that was monitored in ambient air, and there's been several studies that have sort of looked at how well that correlates with black carbon. Again, this isn't PAHs, but assume that it's it's fire that generates both of these things, and they have, going back to the 1960s, kind of a downward trend that they can observe, and it's actually been even used in some studies, I think, by Berkeley or Lawrence Livermore researchers to sort of predict emission factors over time, and you do see a downward trend. So we can't tell you PAHs in specific. The soot in general is coming down.
Great. A couple questions about measurement techniques. So this one's for Dr. Costas. There are measurement techniques to measure ultrafine particles. That was one of the questions that I guess people wanted clarified.
There are measurement techniques. The technology is improving. The whole sensor technology is improving, and slowly but surely it's been focusing, the sensor technology has been focusing more on those more easily measured things, PM levels, ozone, that sort of thing, NOx. The ultrafine technology is a little bit more difficult. You can get special instruments that cost $70,000 or $80,000 to measure them. There are some cheaper ones. The Europeans, the technology they're using is different. They're interested in the numbers of particles. So they have an instrumentation that essentially heats the particles down to a little individual particle and then just counts them. Whereas if it is just a number count issue, that would be that would be great. And certainly the EU is talking about moving towards a count standard. But in the U.S., that technology, there isn't sufficient reason to go to that technology until we understand more about the particle itself, as we know it being highly complex with other organics.
So if we were going to measure something about ultrafines, what do you think we should measure? Number, mass, surface area? So this is a question here that in terms of what's the most important sort of property to try to measure.
Ideally, one won't know it all, right? Measuring just number concentration is rather easy. Even for this ultrafine, we have CPC, condensation particle counters, which are cheap. They don't cost $500,000, easy to deploy. We have even mass spectrometry-based techniques, which allows us to look at composition of particles. It's not individual particles, but more of a bulk by collecting them on little cold finger or some sampler and looking at average composition of these small particles. So we are continuously making progress, even with single particle analysis. We're trying to push it smaller and smaller. We are down to 30 nanometers or so, but we have ways to go. When you're looking at number concentration where this peaks, we have ways to go. When we think about surface area, which is important from health effect, especially, when you think about fractal soot particles and the same size of spherical particles, the volume of fractal soot particles is order of magnitude lower, but surface area is order of magnitude higher. So one has to keep this property, including this fine structure of ultrafine particles, in mind.
Anybody else want to comment on what they think we should be measuring in terms of ultrafines?
I just want to say I agree with what Dr. Zeleniak has just said, and that is that begin with something simple, that way you can measure particle number. And there are lots of instruments which are not that expensive. Condensation particle counters, scanning mobility particle sizers, Moody, et cetera, techniques to do that. And I think that if you then couple the measurement of particle number with a simple assay of some of the biological pro-oxidant activity of a particle, such as the DTT assay or a derivative of that, you will have two parameters that I think will give you a lot of data. It will give you a lot of data in those areas where, you talk about it is being said that we don't have the epidemiology. Well, how are you going to have the epidemiology if you do not try to measure at least something on which to base your analysis? And I think that this could be implemented in relatively short term while more advanced technologies, could be produced. But we could get to the point of getting particle numbers and some sort of activity analysis in order to try and make decisions.
Excuse me. I'm Reed Detchen with the Energy Future Coalition. We've heard a lot about diesel today. We haven't heard much about gasoline, in particular about whether there is a role of aromatic compounds in disproportionately contributing to the fine particulate problem. We observed that the recent episode in Paris where there was the serious smog conditions that caused them to limit their transportation, not necessarily related to that, but earlier Paris research that was based on particle count, as I understand it, attributed a significant portion of that to the presence of aromatic hydrocarbons in gasoline, despite the fact that Paris is a much more heavily diesel environment than the U.S. is. Does anybody on the panel have a comment on that?
So importance of aromatics, presumably in secondary organic aerosol formation.
Well, I understood the question to just also is in addition to diesel, does other vehicular emissions have an important role? And I think the answer is yes. When we started out, of course, we started on the premise of a lot of observations that have been made with diesel, but in doing studies along freeways, which is predominantly used by light-duty vehicles versus heavy-duty vehicles, going into tunnels, going into proximity of airports, getting into areas near the Los Angeles port, it is very clear that the formation of ultrafine particles with semi-volatile organic components, especially the SOAs, are also related to non-diesel vehicular emissions as an important source.
I mean, I can just add a couple things. I've done a lot of work on that particular topic, and a lot of models have a very hard time predicting the amount of secondary organic aerosol in the atmosphere. And so often you'll see very large percentages in model predictions, but they'll be significantly under-predicting what's actually in the atmosphere. So you have to take it with a grain of salt sometimes, the model predictions about the relative importance of organics, or of aromatics, I think. I think they're a very important class of SOA precursor, but sometimes these percentages, I think, inflate them. The work that we've done with dilute vehicle exhaust looking at SOA formation, certainly there is gasoline vehicle exhaust is surprisingly potent at making SOA, I think, from what we've seen. It's not clear that that's related to the aromatic content of the fuel, but more work needs to be done there.
or a very large amount of the PAHs and SOAs and ultrafine particles are essentially absorbed by soil within a fairly, just a few hundred feet of roads, if they're to the extent that they're mobile sourced and coming from vehicles. But Dr. Simonitch is talking about the Chinese Olympics and the forest fires in Siberia suggests to me that that they go up into the atmosphere, that they are global, and that they're circulating globally. And Dr. Zelaznik said that SOAs serve as vessels for long-range transportation of PAHs. And I'm wondering if those two things aren't kind of in contradiction, or to what extent is this stuff floating around in the atmosphere, and do we know that?
We know that small particles survive many days in atmosphere, especially when they get in free troposphere, they undergo long-range transport. We observe biomass burning particles coming all the way from Asia, including particles containing PAHs. So there is clearly deposition. I assume this is what you were referring it And these processes are often size-dependent. Large particles deposit, and the settling velocity and lifetime is much shorter than small particles. But small particles travel long distances, as data show.
I would just add that PAHs are also hydrophobic, so they're attracted or bind to soils. So in a road scenario, you will see decrease in concentration, from the road to further distances away, and some small fraction may enter the atmosphere, enter higher altitudes in the atmosphere and be transported. So both of those are true.
I would just add, I mean, it's certainly true the small particles are transported, but, Saharan dust is measured in Florida. So even large particles make it in almost a countercurrent pattern, depending on however the air masses are moving. It's interesting, especially with the near road, we've done a lot of near road studies. And, the typical way of measuring exposure is to run down to Lowe's and get a tape measure, how far are you from the road? And, the farther out you are, the lower the concentrations of the ultrafine particles, but also the lower the concentrations of NOx, CO, and often overlooked is as cars and trucks are running over roads, they're grinding up the material on the road, generating primarily coarse particles, which contain, PAHs that have deposited there, lead from years ago, metals from engine wear, et cetera. That's high near the road, and guess what? It drops off with distance. So it's interesting when you look at what we're looking at. We have to question ourselves as scientists. Are we looking under the lamppost, or is our hypothesis being self-sustained? I mean, I think that's why I think there's so much research needed in this area. You see along roads oftentimes barriers built to minimize not just road noise, but exposures. But those barriers, and we had a workshop a couple years ago at EPA with barriers that show that you can actually lift an air mass and transport it hundreds of yards. Buildings do the same thing when you have road canyons. Trees actually are pretty effective because of the surface area that they provide. So it's not an easy question. To add to which, on the biologic side, where they've actually done particle deposition by coarse, fine, and ultrafine in human subjects, the deposition of ultrafine particles in terms of proportion is the same as coarse particles. Deposits largely in the upper respiratory tract. Ultrafine particles are close to the size of gas molecules. They bounce around, so they deposit like crazy in the upper respiratory tract, in the larynx, and in the bifurcations of the airways. And if you have disease with constriction of those areas, you'll have more deposition. The same happens with coarse particles. Yet we're not spending a lot of time on coarse particles. So this coarse particle thinking is almost where ultrafines were 15 years ago. At first, everybody thought coarse particles were just junk in the air, don't worry about it. But that's not the case. So it's still a wide open issue.
Let's see, we'll take one more from the audience, and then I definitely want to, each of you, I want to have your what you think research needs are. So we're going to do that at the end, but we'll do one more from the audience.
Thank you. My name is Steve Vandergreen with ICM, and this isn't per se a question, but I hope it generates more comments. As we look at measuring real-world emission rates, I think there's a tool that we would like to recommend that probably should be looked at is the fuel's propensity to form the particulates and the variations you will see in consumer fuels, because there is a lot of variation in consumer fuels in one metro area to the next. And even the autos comment now that even within the test fuels, they have to pay a lot more attention when they're trying to fine-tune these vehicles. So as we look back at a lot of these studies we've been looking at that take benzene or aromatics and the pH formation and growth within nucleates to UFPs, we've looked at Toyota and their evaluation of diesel. We've looked at Honda and their evaluation of gasoline. And Honda actually came up with a predictive model index for the propensity of fuel to create the ultrafine particulates. And we've used that quite a bit. So going forward, I think there's a need, whether it's automotive studies or it's your real world data, that you may want to apply this to understand the fuel composition in both gasoline and diesel, because you are going to have a lot of variation. We can double, triple PM emissions just how we order our test fuels. So I think there's a strong value of looking at the double bond equivalents of aromatics as they contribute to PAHs, UFPs, and then onto the SOA. So I guess I'm recommending a tool rather than asking a question here, but I think fuel composition from test to test is absolutely needed. So thank you.
And I think some of the data that was presented definitely demonstrated that, I think, today. Okay, well, we're almost to lunch. Everybody wants to go eat. We've got 4 minutes, so 1 minute, or, sure. Anybody want to comment on that? Higher ethanol blends? I think specifically you're interested in gasoline, not diesel, not biodiesel.
Yes, we're talking about gasoline.
Yeah, okay.
Yeah, I'll mention a couple things carefully.
Carefully.
Carefully. So, well, I'm not speaking for policy here. You know, I'm a scientist. I oversee the research that's ongoing. We have been doing some work with different ethanol composition. Lost something. Is it back? It's back. So we've done some work, and in the diesel mixes, this is unpublished data. Some of it was presented at the Society of Toxicology meeting last week. With higher concentrations of ethanol, some of the measurements, some of the allergenicity, some of the transformed salmonella cells they use for cancer predictions, et cetera. However, I was amazed at how many presentations and posters that were there that showed the opposite. So it was pretty much an even split. Depending on the mixes, the compositions, the different kinds of fuels that were being blended, there were different health effects. Again, this leads back to this research that we need. And at the same time, you know, I reflect upon years ago when we added what was it to the alcohol mix that we put in California fuels?
Dimethyl ether.
It was dimethyl, yeah, DMT, I guess. And, you know, the sort of the life cycle aspect of things is something that sometimes we don't fully appreciate. You know, are we prepared right now? We certainly weren't prepared when DMTE put it in tanks that weren't prepared to handle that kind of miscibility of that ether, and it got out into the groundwater. So I think that there are consequences, and there are practical consequences, there are chemical consequences, and I think that's where the research is. To say that because we did this study that we showed less of an effect here, the rule of unintended consequences is one that comes around time and time again. So. Well, that's true anywhere. That's true on any issue. Absolutely. Absolutely.
You know, I cannot talk about policies. I could only talk about data and limited data set, which we did on these new engines which are using ethanol blend, like DC engines, gasoline engines. And what we observe is that when you add a little bit of ethanol, it has very little effect on number concentration or size of these particles. I presented, for example, data for pure gasoline for E20, which has 20%, and then we went to E85, which has 85% of ethanol. And this is where we saw in remarkable distance, 2 orders of magnitude reduction in number concentration, and even larger reduction in mass loadings because these particles are smaller. So, as I mentioned, it's limited data set. We looked at maybe at 30 different engine operating conditions, and in all cases, 3 different fuels. And in each case, we observed that very large number of ethanol in fuel content makes very big difference. And it goes back to fundamentals of combustion processes, which I'm not exactly sure where this switch is occurring, but we do observe big differences.
Anything else on that one? I mean, I would say we've looked at fuel reformulation and SOA formation in diesels, biodiesels, different blends of aromaticity in diesels. We haven't seen a strong correlation of SOA formation with fuel composition. We've done work in gas turbines where we've looked at that, and we've seen more relationship. I think it's a very interesting question thinking about ethanol content. That hasn't been investigated that I know of in terms of doing the kinds of empirical studies we need to do to understand what the impact is on SOA formation. But I think there is some evidence that it might be important.
I would just add that it's very difficult to simulate the atmosphere in the laboratory. And so a question like this can really only be well addressed if we have long-term monitoring to study time trends and linking those with changes in fuel. And we don't currently have that.
Anyway, so I guess we're a little bit over, but I still want to see if folks can we'll just take another 2 minutes of your time to just see research needs. I mean, that was a question that a couple of people asked here, and what you would think the highest priority sort of research need, just 1 or 2, not a big sort of laundry list. If we could just go down the panel really quickly, I think that would be sort of a useful kind of capstone to this exercise.
I guess I think that the exposure aspect is a major unknown right now, and developing techniques for assessing exposure and relatively inexpensive measurements that you can associate near road as well as with other related issues. I agree also, can we use a biologic tool as well, DMT, that works well in California, doesn't necessarily work well elsewhere. There's a big study in Europe, the whole set of organic oxidant markers that didn't work particularly well, but it's a potential avenue that where we need some work.
Elizabeth?
I think in the U.S. context, I would vote for improved characterization of ambient environments, so particle size distributions, not only of particle mass number, but also of the constituents like PAHs, and something that we didn't hear about very much today, but trace metals, trace elements that are also associated with some adverse health effects.
I think some of the future needs I see we're starting to work on already, and I think that's PAHs as a really complex mixture, including with metals, and mixtures are difficult to study, but that's the real world. And then long-term trends in both composition and concentrations over time. And most of the PAH measurements in the ambient atmosphere have been done on PM2.5 or PM10 or even TSP. So really there haven't been detailed measurements in ambient air on UFP.
Great.
We'll be agreeing with some already suggestions that we need to have more characterization techniques to characterize the small particles, and especially pay attention to these new generation engines, because right now with these new regulations on fuel efficient engines, companies making many either new combustion strategy or totally new engines using different fuels, and in many cases what produced by this new generation engines is not clear. We spent quite a bit of time studying diesel engines. We did incredible job using diesel particulate filters, reducing emissions. And right now, so many different companies working on this new generation engines, and what they will emit under different conditions is not clear.
Dr. Nell?
You know, so I would say at the early phase is implement immediately exposure activity measurements of even if it's not perfect, to study human health effects. And longer term, develop the more advanced technology to monitor the ultrafine particles and their activity as a real form of readout which you can use throughout areas that are impacted, especially urban areas. And that means you have to move away from centralized areas of air pollution measurement to also doing it in communities and areas where the people are impacted the most.
Great. All right. Well, let's give our panelists a good round of applause here. And thanks to the audience for all the excellent questions. I apologize we weren't able to get to everyone. My understanding is lunch is right outside the door, and we're going to reconvene at 1:30. So thank you, everybody.